Alright, so to continue on with radioactivity and nuclear chemistry, we are going to now talk about fission and fusion, which are types of chemical reactions that go along with radiation. These are the types that you guys hear most often. These are the types that most people are afraid of. First of all, there are two main types. Fission deals with the splitting of a large nucleus into two smaller, more stable nuclei. And then we have fusion, which is when you take two small nuclei, combine them to form a heavier, more stable nucleus, and in the process you are going to release energy. This is actually what happens on the sun to get all of the energy that the sun produces. So for comparing fission versus fusion, fusion is combining and it produces a whole lot of energy, and fission is actually the splitting up, and although it does produce a lot of energy, it's nowhere close to the amount of energy that fusion produces. So let's talk about fission for a little bit. Fission is the type of radioactive decay. This is like nuclear power plants that we do on Earth. Usually when we're dealing with fission, we're dealing with uranium-235 and plutonium-239. These are the only fissionable isotopes that we have learned how to control and manage in a useful way. And there are 5 parts to the process. So basically we're going to take uranium or plutonium and we are going to break it up into smaller, more stable nuclei so that we can harvest their energy. Again, we do this in nuclear power plants. So basically what happens is a neutron reacts with a large nucleus, in this case uranium or plutonium. In the process, energy is released as well as 2 smaller nuclei and 3 additional neutrons. What is so dangerous about fission is these 3 additional neutrons will go on to hit another uranium or another plutonium atom, which then will release more energy, release 2 smaller nuclei and 3 neutrons. Those 3 neutrons will go on to hit more large nuclei such as uranium and plutonium, and the process just continues over and over and over again. This is what leads us to something called a chain reaction. So through fission, these extra neutrons are released and they go on to hit other fissional isotopes like I was just explaining. This creates something called a chain reaction. So pretty much as long as there is a source there, as long as there is uranium, as long as there is plutonium there for the neutrons to hit, this reaction is just going to continue and become more and more violent or reactive until all of our plutonium or uranium is gone. This is an uncontrolled reaction. It can release enormous amounts of energy in a fraction of a second. And again, if you remember from the first day of notes, once you start a reaction, there's really no way of stopping it. We cannot change it with temperature. We cannot change it with pressure. Basically, once a fission reaction starts, it'll just continue until there is no more plutonium or uranium left to react with. Okay, so what's the point of using nuclear fission? Well, we use it because it's a great way to harvest energy. We can use a very little amount of fuel in order to produce a lot of energy, unlike what we do now with coal power plants. So some of the advantages of using fission for energy is, first of all, it would pay for itself in 10 years. So the cost of putting up a power plant, the cost of the uranium, the cost of the plutonium, the operating cost of the plant, so on and so forth, would easily be paid off in just 10 years of service, which is nowhere close to how long it takes us to pay off the production of a coal power plant. Secondly, we need a very small amount of the reactant in order to produce massive amounts of energy for a long period of time. So to kind of give you an example of how much you will need, if I were to take 5 grams of uranium, which is approximately the size of a small paperclip, it would create enough energy to run the city of Springfield for over 6 months. So that when you try to compare that to how much coal it would take to run Springfield for 6 months and our normal power plants, the amount of money we would be saving, the amount of waste we would be preventing, the amount of energy savings we would be getting would just be outrageous. But again, there's always a negative. So some disadvantages for using fission is, first of all, the waste. What are we supposed to do with our radioactive waste? What are we supposed to do with it? Where are we supposed to go? Because even though we're only using 5 grams or a small amount, after it's used up, it's still producing radioactive waste. Everything that has came into contact with it is radioactive waste now. So then we have a whole, how are we going to store it? How are we going to prevent radiation from making people sick, so on and so forth. And if you remember, the only way to protect yourself from gamma radiation was through concrete and lead. So unless you want to build up a whole bunch of concrete and lead storage facilities, it's going to be hard to protect us from the waste. Secondly, fear. Most people are afraid of the idea of using radioactivity for the fear of accidents. Like, what would we do if there was a problem? Because nuclear reactions are so unstable, because that's the whole point, is that they're trying to become more stable. That's why they undergo radioactivity. What would happen if we lost control? What would happen if a chain reaction happened and there was no way we could stop it? So there is a fear component. And then again, even though it would pay for itself in 10 years, on average it costs approximately $20 million to build a fission power plant that could work in a reasonable sized city and provide the amount of energy necessary. So, is using fission safe? First of all, there's only been one major nuclear accident in 50 years, and that was in Chernobyl in 1986, before all of you were probably born. Basically, what happened in Chernobyl is one of the reactors lost power and therefore was not properly cooled, causing a steam explosion. Okay, what happens is when the steam then exploded, this explosion released a great amount of radiation into the atmosphere, and therefore everyone who was exposed to the radiation therefore got sick or had some sort of radioactive or radiation poisoning, so on and so forth. And if you're exposed to a lot of radiation, it can affect your health pretty severely, and especially, not only that, but it can affect your ability to reproduce. So you may not see the effects on you at that moment in time, but that's when you start getting birth defects and so on and so forth in the next few generations. And this is the only accident where radiation was actually released into the atmosphere. So I'm sure there have been accidents or things along the way, but for the most part, they have been contained. This is the only one that was not contained along the way. Okay, so let's look at what a nuclear fission power plant looks like. Again, it is efficient and its initial cost is very expensive. Basically, how a nuclear reactor works is we have these control rods right here. This is going to be your fuel. These are going to be your, basically this is going to be your plutonium and your uranium. And basically this down here is your neutron-rich water. So these control rods are lowered down into the neutron-rich water. And again, the neutrons are what cause the chain reaction to start. They react with the fuel, and then it creates energy. The energy then heats up this water. So then you come over here and it heats up this water, which then produces steam. The steam then rises and goes through this tube, and as it starts to condense, it turns the turbine, which then turns the generator. Over here we have the cooling tower, which then cools the water in here. It then condenses back into water. The pump pumps it back up here, and again we get water, which is then heated from our energy that is being created over here. And it is then goes to steam, runs the turbine, turns the generator, cooled back down, pumped back up there, heated back up. It just goes over and over and over again. Over here, the control rods, this is our neutron-rich water. The more water we have, the more reaction, the more energy. So even though we cannot control chain reactions, this is kind of our way around this. We can control how much fuel we give the reaction. We can control how many fuel rods are in the reaction. So even though we can't control the chain reaction itself, we can kind of sort of control how much sample we have, how much fuel we have in the container. So, heat from nuclear reactors is used to produce electrical energy, and there are 5 components of the power plant that I was just showing you. First of all, you have to take into consideration shielding. How are you going to shield your workers, the environment, the town that it's in from the radiation? Again, most radiation has to be shielded with 6 feet of concrete and lead. Secondly, fuel. Where are you going to get it? How are you going to maintain it? How are you going to store it? What are you going to do with the waste? Third, You need your control rods. This is how, even though we can't control a chain reaction, this is how we can slow it down and speed it up, just by using control rods. We have our moderator, which is how many neutrons can be in access to our sample. And then last but not least, we need a coolant somewhere along the way to cool the steam so that it keeps the reaction cool. Oftentimes this is just water, which is why nuclear power plants are found close to rivers and streams and lakes, so that we have plenty of water to use in the process. So here we have that same picture of our power plant, and this time around I have added the dome. The dome is what houses the core, which you can see it right here, this gray line that goes around. And if you remember, this is where all of our fuel was. This is where the reaction is technically taking place. So this is probably going to be our 6 feet of concrete and lead protecting the employees and the town, so on and so forth, from all of the radiation. And then we have the core, which contains the neutron-rich heavy water and fuel rods and our control rods. So right in here is where the reaction, and this is called the core. So here's our core, and here is our dome protecting us from the radiation. And if you notice, all this over here doesn't need to be under the dome because none of this is technically affected by radiation, because all of the radiation stayed over here. Alright, so now that we've talked about fission for a while now, let's talk about fusion for a little bit. Fusion is the opposite of fission. Fission is where you take a big nucleus and you break it down into smaller using neutron. In fusion, you actually take two smaller nuclei and you combine them to form a heavier, more stable nucleus, and in the process you release lots and lots of energy. This releases a significant amount of energy, a lot more than that of fission. This occurs on our sun and in other stars, which is why our sun produces so much more energy. So basically what happens is we take two different forms of hydrogen. So we have hydrogen 1, which is the hydrogen off the periodic table, which is just a proton and a neutron. And then we have a neutron-heavy hydrogen, hydrogen 3, which technically has 2 protons and 1 neutron. Or no, 1 proton and 2 neutrons. And basically what happens is these two things will collide and they will combine to form helium, which is 2 protons, 2 neutrons, which gives it a mass number of 4, which if you look at the periodic table is the helium found on the periodic table. It has a 1-to-1 neutron to proton ratio, so therefore it is relatively stable. But in this process, it releases a lot of energy. So some advantages to fusion is, first of all, clean burning. So we wouldn't have to worry about nuclear waste. We wouldn't have to worry about what are we going to do with all of the other things that can be often produced whenever we are creating power. And also, hydrogen is very, very common. There is an abundant supply. So we wouldn't have to worry about where are we going to find enough of this to produce the energy, because hydrogen is so abundant. I mean, hydrogen is the main part of water, so think about how much water we have. That's how much hydrogen we have. Some disadvantages to fusion are, first of all, it requires very high temperatures. Temperatures so high, I mean, think about, fusion is what happens on the sun. So think about how hot the sun is. That is what I'm talking about when I say high temperatures. So if we were able to do fusion on Earth, I mean, technically it would vaporize the planet. And I know that sounds pretty extreme, but it would require such high temperatures, and again, it would be a chain reaction. There would be no way to stop it. And then last but not least, it would cost so much money to make a fusion reactor, to make fusion work, that it would cost significantly more than the amount of energy we would get out of it. So it's not as easy for us to control like the fission reactions are. Alright, so now that we have talked about fission and fusion, hopefully you have a good hold on what all that is. So now you guys are going to get started on your classwork or your homework, and hopefully you guys do a great job at it.